Hello everyone, ladies and gentlemen, hackers and script kiddies. I'm Tobias Rook, and I'm glad to be able to talk here at Grehack. And I'd like to tell you something about Linnea, the project I've been working with Miranda Mowbray at HP. And basically, it's about how to select clients from a network that have some specific type of malware. So suppose you're a very successful hacker and you manage to get a zero amount of malware infected, a zero amount of clients infected by a malware, Super William style. Your malware connects to the domain you've hard-coded into your code to connect to your console that it can execute your commands. Well, but this might work for some time, but then people find out about the domain, for example, mymalware.com, and what they do is that they blacklist it, so which blocks any connection to a console, and you can't communicate to it anymore. But as you're a very smart hacker, you come around with a solution, and you use the infinite power and love of RNGesus, and what you do now is you generate an enormous amount of randomly generated domains, and using domain generation algorithms, DGAs. A seed for a DGA could be the current date, the recent Twitter trends, or Chancellor Merkel's pants, though the last one would be rather impractical. So, what you do now? The first two, by the way, are actually used in practice. What you do now, you connect to them all, and yeah, boy do they fail. This is since you only register one of the domains, only one, and only one will resolve, the one you registered, and that way you can connect. That way you can connect to your console. Why is this working? As cybersecurity experts like to say, one does not simply ban 1,000 domains a day. And, hooray, you managed to get the world ruled by millions of submissive bots. But yeah, then there are people like me or Miranda who try to break this, to try to prevent this from happening. And what we do is we stop it using SQL queries, which I will explain now. So the overall architecture is like this. You're having both benign and infected clients are going to do all different kinds of domain requests, and they will all send it to a DNS server. The DNS server will evaluate the query, and it will either respond with an IP to connect to, or with an X domain if there's no such domain. If you know DNS packets, that should be all very clear. And most larger enterprises have their own DNS server, and what we do now is that we install a packet capture on that DNS server to track all the incoming and outgoing requests. So we store this in a database. Our choice was Vertica DB due to its high performance. Yeah. Snowden would be proud of us. I should also say that we're doing this to prevent malware from spreading, not to track every thought of every human being. That's already NSA jobs anyway. So next, on our big data for a security server, BD4S, we run an SQL query every 2 hours for each malware type. And what it does, it will give us a list of infected clients. But not only that, since we craft an own query for every malware type, we also get the type of malware. this then gets reported to a security operations center, and they resolve the problem either automatically or manually. How I imagine it is that they roll around in office chairs wearing wizard clothes, pointing the magic wand at computers, chanting "Reparo." But enough on that. Yeah, one DGA I'd like to explain is a Matsnu. Its most dominant feature is that all domains are human readable, as you can see here. They don't make a lot of sense, obviously. For example, tailtalk-alarm.com or towelbecome-maintenance.com. But that's not too easy to find out. What's easier to find out, though, is the abnormal number of hyphens, coupled with the fact that most of they won't connect. So how do we detect this? Yeah, let's all hold onto Pokeballs and try to catch them all. Okay, I gotta catch them all. So in the inner query, we select the pattern matching with a regular expression. We also check that they are non-resolving, it is the next domains. Then we count the number of hyphens, if there's one or two. And in the next superquery, we check how many fulfill the surrounding predicates. And in the last superquery, we check if there's at least some certain number of domains surrounding each domain. Yeah. If this seems a bit messy, then you're on the same page with me. For that reason, we invented the language. Linnea for the SQL, making a language just for the heck of it. Looking closer, we can see that heck can mean a lot of things like disorder, mess, entropy, or hell. But here it means to make things easier. So this is exactly the same query, but in a different notation. In the first block, you can see that we limit our time frame to 2 hours. We select only those that are non-resolving, as NX domains. And then we match only those that have letters and hyphens with a length of 11 to 23 suffix.com. In the next block, where the interesting part is, the syntax is very linear specific with the brackets. I'll explain that later. We check if there's at least 25 queries per client within 1 hour forward and proceeding. We check if there's at least one or two hyphens, at least 20 domains with 1 or 2 hyphens per client within 1 hour forward and proceeding. And we check if there's between 9 and 200 with 1, and at least 9 with 2 hyphens per client within 1 hour forward and proceeding. So let's execute our query. We run it into our database, and this is some actual data I got from a client. And you can see that it's kind of working. Also note, if we go through the list, you can see that some domains don't contain a hyphen, since surrounding domains contain a hyphen. For example, professorlewis.com, no hyphen there. So if you reverse engineer Matsnu, you find all the words that are used by Matsnu to generate these domains. And the regex to do that looks like this. It's a lot of words, and if we zoom in a bit, you can see that they're all some type of English noun or verb. So if we highlight the results using this regex, then we get something like this, and you can see that all match, except this one here, timetankstel.com. And here at the bottom there is a sandwich. This is since sand is also a verb and the highlighter doesn't use a greedy search. But the fact is we are not looking for the dictionary, but still we get results that match the dictionary. So enough for the examples. Let's have a look at the. Do I have something to drink? Sorry, thirsty. At the so-called teabag syntax, as I named it. It's very useful for analytic evaluation. It basically counts the number of surrounding domains from a domain matching some predicates. So if we have a teabag like this, where we have the properties A0 to AN with time frame T and predicate P, we go through all remaining domains within the time frame T. Then we keep all those that match all properties A0 to AN with the current domain. For example, this could be the IP of the client. And also note that this is very similar to the group by statement in SQL. Then we keep all the domains that fulfill P, and then we return the number of remaining elements. As an example, this should go somewhere. No. Okay. This syntax here, it says that there should be at least 20 domains within 1 hour forward and preceding per client that have the suffix .com. So if we compile this to SQL, you can see that it's a lot more complicated. And yeah, you can look up the specification of the count over syntax, but it's essentially exactly the same thing. And generally, we can observe that the Linnea syntax is way shorter than SQL, although it's a bit less flexible. However, what we found out is that it's flexible enough to capture all the malware types that we've found so far. So, yeah, you might be asking yourself now, how do I craft a linear rule? And spoiler alert, it's not involving 4 iron ingots placing around a redstone dust. Instead, we split. If we get data from a computer that's infected by some malware, we split it into 2 layers. Basically, we split our query into 2 layers. One which is fast to compute, throwing away a lot of data. One which is slower to compute. So in the first layer, we first check if the domain is non-resolving. Next, if we analyze the domains that are in our set, then we check for the allowed character set that are queried, for the allowed toLengths, the number of characters before the suffix, and for the different allowed suffix. And we combine all of these into a regular expression. We also count. What we could also try to find out as property is, for example, the frequency of vowels or something like that in a domain, as we can see later. In the second layer, which is a bit slower to compute since it aggregates over multiple domains, we check if there is a minimum number of domains within time frame, or if there's a minimum number with hyphens of numbers, or a maximum number with a certain suffix. Okay, so what you should also note is that if there are many domains, if there are many different malware families, you have to try to avoid confusion with each other. You'll see an example of that later. But if you obey these rules, then it's not too difficult to write linear queries. As an example, let's have a look at this malware here. It's, well, the string in front of the suffix can be the same for different suffixes. We can use that in a Linnea rule, and it gets really tidy. And the last predicate, you can see that we can combine the tbag syntax. So we first check if there's a counterpart for the current domain, and then we check if there are at least 10 domains with a counterpart for the current domain. Yeah. Another example is push-to. You can see its dominant feature is that all domains are Kazakhstani domains, and also the vol frequency is slightly higher, and which makes it pronounceable more or less. But we can use that in a linear query as well. For example, here again, time frame 2 hours, an X domain. But in the last predicate, in the first block, we check if the amount of the percentage of vowels is larger than 35%, which is a pretty good empiric estimate. Also note that push-to only queries KZ domains, but in the regular expression we also leave in com, in, info, and net. This is since another DGA called flashfake queries com, in, info, KZ, and net, and we leave those in only to filter them out in the next block, where we check if the number of KZ domains is larger than any of the other domains. So, yeah, these are all the DGAs we wrote queries for. You can find them under the following URL. You can find the URL in the paper if you want. And we also supplied a compiler written in Python to compile Linnea to SQL. So what are our results? We tested our environment on the 11th August of 2015. We had 18 million NX domains entries in our database. We had 300,000 distinct non-resolving domains by 69,000 clients. We ran everything on a Vertica database on an HPDL30 configuration, if you want to explain the performance, since the performance is actually pretty high. For 2-hour time slots, we have 2.1 seconds for the slowest query and 0.9 seconds for the fastest query. That is, if we run all 16 rules consecutively, we need 19.3 seconds in total. That is, keep in mind that this is for 2-hour time slots, and if regarding the average time, if the server would be 100% busy, we would need 3,000 queries, and if there would be a new DGA-based malware every week, that would mean that it would take 57 years to make the server 100% busy, and until then I would die due to my unhealthy lifestyle. So this number is sufficiently large. And the results, we did an independent analysis by eye, and 10 malware families were present out of the 16 we watched out for, or we wrote queries for, and all of the malware families were actually detected by the queries. However, we didn't identify 2 clients, and we had 1 false positive. However, we classified 72 clients correctly. So, how do we compare versus machine learning or using pure SQL or lexical analysis? On the pro side, we can tell you which malware is present, unlike most machine learning approaches or lexical analysis. Also, it's pretty transparent what we're doing. You can always understand what the query is running, since we have no fuzzy classifier. Also, writing linear rules isn't too difficult compared to pure SQL, as you could see. On the con side, however, as I said, our system only works for known malware, and we have to design a new rule for each malware. This doesn't happen automatically, and we have to do it by hand so far. As a conclusion, the pros occupy more space than the cons. Therefore, our stuff is clearly very good. Yeah. I'd like to acknowledge Claudius Wild for the magic wand, and thank you for your attention.
Thank you, Tobias. We have time for one or two questions before playing pinball. Yes?
Hi, thanks for the talk.
Yes, your question?
Yep. So you are storing all your DNS logs in an SQL server, and you are doing SQL queries to query the data. I was wondering if there is a more efficient way of storing your data, as it is the time factor is really important for your use case, and there are databases that are very well suited for this kind of data. There's many solutions. Don't you think that by storing all your DNS logs in specific time-friendly databases, you will be able to have better performance?
You have to keep in mind. Okay, you have to keep in mind that the Vertica database is more or less optimized for exactly this task of inserting a lot of stuff and then doing analysis on the recent data. Does this answer your question?
More or less. Okay. I was just wondering.
Well, if you want to do stuff like this, the Vertica database is more or less optimized to do this kind of stuff.
Okay, so on very big amount of data.
Yeah, exactly. Okay. A big data analysis tool.
Okay.
There might be other tools, but let's say we got that database for free and it worked pretty well, so
okay,
we used
thanks.
that.
Another question, comments? Okay, indeed, I have a question. Are you sure that the expressivity of your language cover all the possible requests in SQL?
Do you mean that everything we write in SQL can also be written in Linnea? No, we can't yet. But if we put more research on that, we could maybe make a replacement for SQL. But at the state of writing this, it was not the goal to do this. And we focused more on the research on the malware families. But you're right, we could make a language that replaces SQL in a more simpler way. More questions?
Okay, so let's thank Tobias again.